In this video tutorial, I am going to discuss about enzyme inhibition. So let's first talk about enzyme inhibitors. What is enzyme inhibitors? Enzyme inhibitors are the substances which carries out two work or two peculiarity. First, it binds with enzyme E, and second, that once they are bound with the enzyme, they decreases the catalytic activity of that enzyme. So such substances are called as enzyme inhibitors. In a biological system, there are total 3 different types of enzyme inhibitions are seen. The first one is the reversible inhibition. The second one is the irreversible inhibition. And the third one is the allosteric inhibition. In case of reversible inhibition, the inhibitor molecules bind with the enzyme by the non-covalent bond. We know that non-covalent bonds are a weak bond. So this inhibitor molecule can be easily separated from this enzyme molecule. And there is one procedure, that is a dialysis, by which we can separate inhibitor from the enzyme molecule. Whereas in case of irreversible inhibition, what happens? Enzyme molecule tightly binds with the enzyme molecule. And it is a tightly bind because the bond is a covalent bond, which is a stronger bond. So because of the stronger bond, inhibitor molecule cannot be easily separated from this enzyme molecule. So this is kind of a permanent inhibition, right? And here the dialysis process cannot separate inhibitor from the enzyme molecules. Now let us talk about the subtypes of these 3 major types of inhibition. In case of reversible inhibition, there are many different types of reversible inhibition. But most commonly, in a biological system, we observe 3 different types of reversible inhibition. The first one is the competitive inhibition. The second one, that is B, is the non-competitive inhibition. And the third one is the C, uncompetitive inhibition. In case of irreversible inhibition, there are no many subtypes, but there is one special subtype is there, which is called as a suicide inhibition. This suicide inhibition is also known as mechanism based inhibition. And in case of allosteric inhibition, there are no any subtypes. Now, so these are the various different types of enzyme inhibition, and we need to discuss all of them. So let's start our discussion first with this competitive inhibition. So the first thing that we need to discuss is the competitive inhibition. Now to understand about the competitive inhibition, suppose this is the enzyme molecule E, and this cleft, it represents the active site of the enzyme. Suppose this triangle represents substrate S, and about the inhibitor molecule. So in this competitive enzyme inhibition, what happens? This inhibitor molecule is going to be the structural analog of the substrate. So let's represent this inhibitor molecules by with this triangle, but here there is a wavy line, right? So as we can see in this schematic, that inhibitor molecule is the structurally similar or a structural analog of the substrate. Now what happens in this competitive inhibition? This substrate obviously binds at the active site. But here, because of the structural analogy, inhibitor molecule can also bind at the active site. But what happens? Whenever substrate is occupied at the active site, inhibitor cannot bind, and wherever inhibitor molecule is occupying at the active site, this substrate cannot bind. So we can say that between this substrate and inhibitor, there is a constant competition. Constant competition can be there, right? Now, once enzyme binds with the substrate, it can lead to successful product formation. But when enzyme binds with the inhibitor, it does not lead to successful product formation, but it is possible that enzyme and inhibitor when binds, it leads to alternate product formation Q. But this is of no use to us, right? So here, as far as this proper product is concerned, it will not form. So that's how enzyme's catalytic activity is inhibited. Now let's try to mention everything about this in a proper model. See, suppose this is the enzyme. Now this enzyme, as it has two possibilities. It can either bind with the substrate or it can bind with the inhibitor. If enzyme binds with the substrate, then it can lead to formation of enzyme substrate, that is ES complex. And this ES complex formation is the reversible process. Now once ES complex is formed, it can lead to liberation of free enzyme and successful product formation, right? Whereas when enzyme binds with the inhibitor molecule, and we know that at that time it cannot bind with the substrate. So when enzyme binds with the inhibitor molecule, it can lead to formation of EI complex. Now as this competitive inhibition is of a reversible type, so EI complex can dissociate once again into enzyme and inhibitor molecule, right? Now this enzyme inhibitor molecule, most of the time it is a dead end, but sometime what happens, enzyme inhibitor molecule can further undergo reaction and it can liberate free enzyme and altered product formation, that is represented by this Q. But this is not the always case. This is not compulsory. It may or may not occur. But whatever the case may be, this enzyme will remain occupied with the enzyme inhibitor molecule, and so this enzyme cannot lead to successful product formation, right? So based on all this information, we can write down certain important aspect of the competitive inhibition. The first important aspect is that inhibitor molecule is structurally or closely resembles the substrate, or we can say that inhibitor molecule is the substrate analog. The second important aspect is that inhibitor molecules binds at active site of the enzyme. The third important aspect is that here the formation of ES as well as EI, these two complexes are formed. So formation of ES and EI complexes. Now see, as there is a continuous competition between substrate and inhibitor, what will happen if we increase the substrate concentration very high? So at that time it is possible that as substrate concentration is very high, no any inhibitor molecule can bound with the enzyme. So at that time this enzyme can show its maximum velocity. So it is possible to achieve the maximum velocity at very high substrate concentration. So here the fourth important point we can write is that Vmax, that is the maximum velocity of the enzyme, it is unchanged in case of competitive inhibition, right? Now let us try to fit everything into the diagram or into the graph. So when we draw a graph of velocity versus substrate concentration, so velocity V0 on the y-axis and substrate concentration on the s-axis. So when inhibitor is not present, as we had seen in the previous video, the graph will be like this. This graph we had already discussed in the previous video. So this blue line represents that no any inhibitor is present. So at this place, maximum velocity is seen, right? So this is the Vmax. And remember, in the definition of the maximum velocity, it has nothing to do with the substrate concentration. Okay, so at whatever substrate concentration the maximum velocity is seen, we call it as a Vmax, right? Now if this is a Vmax, then the half point is lying over somewhere over here. So this is the 1/2 of Vmax. And at the 1/2 of Vmax, whatever substrate concentration is there, so this is the substrate concentration at the half maximum velocity. And if you remember the definition of the Km, what is Km? Km is the substrate concentration at the half maximum velocity. So this point represents the Km value. Now in case of this competitive inhibition, this inhibitor is added, then what will happen to this graph? Okay, so I will represent it by the red line. So as because of the inhibitor, the velocity will be decreased. So this will be the graph. But as we had discussed, at the sufficiently high substrate concentration, it can reach up to this maximum velocity. And so with the inhibitor, as you can see, this maximum velocity remains unchanged, that we had already written, that Vmax is unchanged. But what happens to this Km value? See, if this is the Vmax, the same point is going to be 1/2 of the Vmax. And at corresponding 1/2 of the Vmax, we can find out the substrate concentration is over here. So the new Km value is this one, right? So here we can see that Km value is getting increased. So here Vmax remains unchanged, but what happens to the Km value? Km value is increased. So this typical or peculiar picture is seen in case of competitive inhibition, right? I think that this graph, by this graph you can understand that why Vmax remains unchanged and Km is increased. Now let's also draw the double reciprocal plot, which is also called as a lineweaver burk plot. Here on the y-axis, we take a reciprocal of this velocity, so here 1 by v0, and on the x-axis we take a reciprocal of the substrate, that is 1 by substrate concentration. Regarding this double reciprocal plot, we had already discussed in one of my previous video. So suppose without inhibitor, this is the line which represents enzyme activity. We know that on the y-intercept is the 1 by Vmax, and the x-intercept is going to be -1 by Km. Now in case of competitive inhibition, what happens? Vmax remains unchanged, right? So this 1 by Vmax will also not change. So this is the point. And Km is going to be increased. If Km is increased, then 1 by Km is going to be decreased. And as it is a minus sign, we need to draw a point near to the 0. So this is the new point in presence of inhibitor. And from this 2 point, we can pass one line. So this red line, it represents that with the inhibitor, such line will be seen. So this is the case of double reciprocal plot in case of competitive enzyme inhibition. Now let us look at the various examples in real life about the competitive inhibition. So now we will discuss about the examples. The first example to discuss is about the anti-cancer drugs. There are several anti-cancer drugs, for example, aminoterine, amethotyrine, and methotrexate. What this drug does, this drug competitively inhibits one enzyme, that is dihydrofolate reductase. This dihydrofolate reductase generally converts folate into dihydrofolate, and dihydrofolate further gets converted to tetrahydrofolate. These both reactions are catalyzed by the dihydrofolate reductase. This tetrahydrofolate is the active form of folic acid. It has many functions, and one of the important function of tetrahydrofolate is for the replication and cell division. So for the cell growth, tetrahydrofolate is required. This folate we take in the diet, but this folate is not directly useful. It needs to get converted into its active form. Now what happens? This dihydrofolate reductase, its natural substrate is the folate. But these three drugs, aminoterine, amethoterine and methotrexate, all these three are the structural analog or structurally similar to the folate. So these drugs occupies the dihydrofolate reductase, and so what will happen? Folate cannot be converted into its active form, that is tetrahydrofolate. So replication and cell division can be stopped. And in case of cancer, this replication and cell division is the major problem. So if we inhibit this, then we can treat cancer, right? So that is how these drugs are useful for the treating of cancer. The second example that we need to discuss is the anticoagulant drugs. Anticoagulant drugs. Here we have two drugs. One is dicumarole and second one is the warfarin. These both drugs competitively inhibit one enzyme, that is vitamin K epoxide reductase. Now the normal function of vitamin K epoxide reductase is to convert vitamin K, which is in the oxidized state, to the vitamin K in a reduced state. Now reduced state of vitamin K is the active form. Vitamin K, which is in the oxidized form, it is not active, right? And this reduced form of vitamin K is useful for the activation of coagulation factor number 2, 7, 9 and 10, and so this factor can causes the clotting of blood. Now this dicumarole and warfarin both are structural analog of the oxidized form of vitamin K. So they competitively inhibit vitamin K epoxide reductase, and because of this inhibition, this coagulation factor will not form and clotting will not occur. So in a patient where hypercoagulability is seen, these drugs can be given. The third important example is about the antibiotics. And here we have one large group of drug which is collectively called as a sulfonamide. Now what this sulfonamide does? Sulfonamide competitively inhibits one bacterial enzyme which is found in the bacteria, and its name is dihydroteroate synthase. This dihydroteroate synthase is only found in the bacteria but not in the human. Now what this enzyme does? In the bacteria there is a para-aminobenzoic acid. This para-aminobenzoic acid, with the help of this dihydroteroate synthase, it binds with the pteridine and gets converted to dihydroteroate. This dihydroteroate further undergoes multi-step reaction to give rise to tetrahydrofolate. And as we had seen earlier, in this case, this tetrahydrofolate is responsible for the replication and cell division. So in the bacteria also, this tetrahydrofolate is useful for the replication and cell division. Right. Now this sulfonamide group of drug, it is a structural analog of this para-aminobenzoic acid, right? So it competitively inhibits this dihydroteroate synthase, and so bacteria will not able to synthesize tetrahydrofolate, and by inhibiting this enzyme we can inhibit replication and cell division of the bacteria. So it will help us for the control of bacterial infection. The next example is of the anti-hyperlipidemic drug. Anti-hyperlipidemic drugs. Here we have statin group of drugs. This statin group majorly involves atorvastatin and pravastatin. This both drug, atorvastatin and pravastatin, competitively inhibits one enzyme, that is HMG coenzyme A reductase. This HMG CoA reductase is found normally in the human, and what this enzyme does naturally is that it converts HMG CoA molecule into the mevalonate. Then this mevalonate undergoes multi-step enzyme catalyzed reaction to give rise to cholesterol. So this is actually a pathway of de novo synthesis of cholesterol in our body. And in this pathway, this HMG-CoA reductase is the rate limiting and regulatory enzyme. And this atorvastatin and pravastatin both are structural analog of this HMG-CoA. So once this enzyme is inhibited, then in our body the cholesterol synthesis can be decreased, and that is how this drug can help to bring down our hyperlipidemia, right? So it is used as an anti-hyperlipidemic drug. The fifth example is about the methanol poisoning. See what happens in case of methanol poisoning. Methanol itself is not that much toxic, but what happens in our body, this methanol is converted to formaldehyde. This formaldehyde is actually a very toxic substance, and this conversion from methanol to formaldehyde is brought about by the enzyme alcohol dehydrogenase. Remember, this methanol is less toxic. So somehow if we inhibit this enzyme, then this more toxic formaldehyde can be prevented. And for that we can take a usefulness of the competitive inhibition. So we have a structural analog of the methanol, and that is ethanol. Ethanol, it is a structural analog of methanol. So ethanol competitively inhibits this alcohol dehydrogenase, and so this formaldehyde formation can be prevented, and this is how ethanol can help in the methanol poisoning. The last thing in an example that we need to discuss is about the gout or treatment of gout. Gout is a condition in which there is increased uric acid production. Remember, this last example is very unique, right? Let's see how it is unique. See what happens normally in our body. The purines undergo catabolism. So by the catabolic pathway, by the multi-step process, purine gets converted to hypoxanthine. This hypoxanthine then gets converted to the xanthine by the enzyme xanthine oxidase. This xanthine can be further converted to the uric acid, and this reaction is also catalyzed by the xanthine oxidase. And we know that in case of gout, there is increased uric acid level in our blood. So we need to bring down this uric acid level. So for that we have a structural analog of the hypoxanthine, and that is allopurinol. Allopurinol, by being a structural analog of the hypoxanthine, it competitively inhibits this xanthine oxidase, right? And so uric acid production can be brought down. But there is one unique aspect about the allopurinol. See, allopurinol is an inhibitor, and this xanthine is our enzyme. And as I told you earlier in the model, that once enzyme inhibitor complex forms, this thing, that enzyme and altered product formation may or may not occur. In case of allopurinol, this altered product formation is there. See what happens when allopurinol binds with the xanthine oxidase. This xanthine oxidase converts allopurinol into alloxanthine. And remember, this reaction is catalyzed by the enzyme xanthine oxidase. This is the same enzyme, right? Now this alloxanthine, it is actually a more potent and irreversible inhibitor of the xanthine oxidase. This kind of inhibition is irreversible and more potent, right? So remember, allopurinol directly inhibits xanthine oxidase. That is a competitive inhibition. But by binding of allopurinol with the xanthine oxidase, allopurinol itself gets converted to alloxanthine, which is more potent and irreversible inhibition, right? So here xanthine oxidase, what it had done, it had converted less potent and reversible inhibition into more potent and irreversible inhibition. So here we can say that xanthine oxidase itself is doing suicide. So such kind of inhibition is also called as a suicide inhibition. Right? Remember, in case of suicide inhibition is a combination of both competitive inhibition initially and later on irreversible inhibition. And as this enzyme by its mechanism, it is converting this allopurinol to alloxanthine, this type of inhibition is also known as mechanism based inhibition. Right? So this completes our discussion about this competitive inhibition. Now let us look at the non-competitive inhibition. So the next thing to discuss is about the non-competitive inhibition. Now to understand about the non-competitive inhibition, suppose this is the enzyme molecule E and this triangle represents substrate. Remember, this cleft is the active site, right? Now in case of non-competitive inhibition, what happens? Inhibitor molecule is not a structural analog of the substrate. So let's represent inhibitor molecule by this. What happens? Substrate naturally binds at the active site. But here, in case of non-competitive inhibition, inhibitor molecules binds at the site other than the active site. So let's say inhibitor molecule is binding at this site, right? So by this binding, one thing is clear, that if substrate binds at the active site, it does not have any influence on whether inhibitor will bind or not, and reverse is also true. Wherever inhibitor is bound with this enzyme molecule, it has no any influence on a substrate binding. So let's show all of this in our model. So suppose this is the enzyme. Enzyme can naturally bind with the substrate at the active site, and reversibly it can convert it to enzyme substrate complex. This enzyme substrate complex can be converted to free enzyme and product formation. As I told you, this inhibitor molecule is binding at a site other than this active site. So it doesn't have any difference whether substrate is bound or not, right? So inhibitor can bind either with this free enzyme. So enzyme can bind with the inhibitor, or inhibitor can also bind with the enzyme substrate complex. So ES complex can also bind with the inhibitor. So basically there is no any competition between substrate and inhibitor. That's why it is called as a non-competitive inhibition, right? Now let's see what will happen when enzyme binds with this non-competitive inhibitor. So it can reversibly form, as this is a type of reversible inhibition, right? So reversibly forms EI complex. And when inhibitor binds with the enzyme substrate complex, it reversibly forms enzyme substrate inhibitor complex. Now remember, this enzyme inhibitor complex, it can later on also bind with the substrate, as there is no any influence of inhibitor on the substrate binding, right? And it can reversibly gives rise to ESI complex. So this is how its model looks like. Now based on this model, we can write down certain important aspects of this non-competitive inhibition, right? The first thing is that inhibitor is binding at a site other than active site. The second thing is that here there is a formation of EI as well as ESI complex in addition to ES complex, right? So here formation of EI and ESI complexes. Here there is no any structural resemblance of the inhibitor with the substrate. So there is no structural analogy. Now here try to understand one very important aspect. In this case, whatever substrate concentration we increase, even at a very high substrate concentration, as there is no competition between inhibitor and substrate, whatever high substrate concentration we take, some amount of inhibitor will be always bound with the enzyme, and that enzyme will be inhibited. So unlike competitive inhibition, at very high substrate concentration, we cannot achieve maximum velocity. So here the very important thing is that Vmax, that is a maximum velocity, is going to be decreased by the non-competitive inhibition. You can compare it with the competitive inhibition. In the competitive inhibition, Vmax remains unchanged, right? Now let us try to understand this thing in a graph. So typically, we draw a velocity versus substrate concentration. So velocity V0 on the y-axis and substrate concentration on the x-axis. And in absence of inhibitor, the graph looks like this. Okay, so let's say this is the Vmax, that is the maximum velocity. The half of Vmax is somewhere over here, so this is 1/2 of Vmax, and the corresponding concentration of substrate is this one. And we know that the substrate concentration at the half maximum velocity is called as a Km value. Now what will happen in a presence of non-competitive inhibition? We know that Vmax is going to be decreased. So let's see that Vmax is over here. Okay, the new Vmax in the presence of inhibitor. So let's draw a graph. So this graph is there in a presence of inhibitor. Now if this is a new Vmax, then this is going to be a new 1/2 of Vmax, right? And the corresponding concentration of substrate is going to be same. So here the new Km value is going to be same as a old Km value. So here we can say that Km value is going to be same or unchanged, right? Now we can look at this Km value at one different aspect. In a previous video, we had seen that Km value is a representation of affinity of substrate with enzyme, right? And here you can see that whenever inhibitor binds with the enzyme, it does not have any influence whether substrate will bind or not. That affinity is not affected, and that is being proved by this graph, and as well as this Km value mathematically it remains same or unchanged, right? So this thing we have to keep in mind. See, so summarily, in case of non-competitive inhibition, Vmax is decreased, whereas Km value it remains unchanged. You can compare it with the competitive inhibition. In the competitive inhibition, Vmax is unchanged, whereas Km value is increased, right? Now if we try to draw a lineweaver and burk plot, which is also called as a double reciprocal plot. Here on a y-axis we take 1 by velocity, and on the x-axis we take 1 by substrate. Suppose in absence of inhibitor, this is the line, and we know that on the y-axis intercept is going to be 1 by Vmax, and the x-axis intercept is going to be -1 by Km. Here in case of non-competitive inhibition, we know that Vmax is decreased, right? So Vmax is decreased, that means Vmax is going to be increased. So let's say this is the new 1 of Vmax, right? And here Km value remains unchanged, so -1 by Km will be the same. So now we need to draw a line between these red dots, okay? So the new line is going to be like this. So such type of shift will be seen in case of non-competitive inhibition. Now let us look at the examples of non-competitive inhibition. So the examples. Now this is not so common in our biological system. Mostly what happens, heavy metals, for example lead, silver and mercury, these heavy metals in low concentration inhibits various enzymes by a non-competitive mechanism. The second important example is the soybean trypsin inhibitor, which is also called as a SIT. Remember STI. Remember, this soybean trypsin inhibitor is the name of molecule which is found in the soybean, and it non-competitively inhibits enzyme trypsin, which is a protein digestive enzyme. So this completes our discussion about the non-competitive inhibition, right? So we had completed this non-competitive inhibition. The next we will discuss about uncompetitive inhibition. So the next thing that we need to discuss is the uncompetitive inhibition. Now to understand about this uncompetitive inhibition, suppose this is our enzyme molecule E and this half circle, it represents its active site. And suppose this is the substrate molecule, right? So when enzyme binds with this substrate, it will look like this. This is the active site of enzyme. This is the enzyme and this is the substrate molecule, right? So the substrate molecule is bound at this place. Now what happens in case of uncompetitive inhibition? When substrate binds at the active site, it creates a new shape in the active site, and in this shape our inhibitor can bind. So remember, this inhibitor molecule, it can bind with the enzyme once substrate is bound. So inhibitor molecule, it is not able to bind with the free enzyme. Why? Because there is no any presence of site. But when substrate binds with the enzyme, at that time new site is created where this inhibitor molecule binds, right? So let's try to show this in our model. So normally what happens? Enzyme binds with the substrate. Reversibly, it gets converted to enzyme substrate complex, and this enzyme substrate complex then further get converted to free enzyme and product formation. Here this inhibitor molecule, it only binds with the enzyme substrate complex. So it cannot bind with this free enzyme, it binds with this enzyme substrate complex. And here also, as uncompetitive inhibition is a type of reversible inhibition, so reversibly this enzyme substrate with inhibitor, it gets converted to ESI complex, that is enzyme substrate inhibitor complex. So here one very important aspect is that inhibitor is not a structural analog, of substrate, right? The second thing is that there is no any formation of enzyme inhibitor complex, right? Rather there is only formation of enzyme substrate inhibitor complex. Only this complex is formed, this complex is not formed. Now what will happen to the Vmax and Km value? What will happen to them in the presence of inhibitor? See, first let's talk about the Vmax. So here, as you can see, there is no any competition between inhibitor and substrate, right? So what will happen? If you go on increasing the substrate concentration, whatever substrate concentration is there, this inhibitor molecule will always be bound with this enzyme substrate complex. So some of the enzyme will always be occupied in the enzyme substrate inhibitor complex, and so the velocity will be decreased. So we will not able to achieve the normal maximum velocity. So here we can say Vmax is going to be decreased. Whereas what about the Km? See, what is Km? Km is a measure of affinity, right? It is a measure of affinity. Affinity between what? Affinity between enzyme and substrate. So what will happen in a presence of inhibitor? So if this inhibitor is not present, what will happen? Some of the enzyme substrate complex will be always there, right? But in presence of inhibitor, in addition to this ES complex, this ESI is also there. And see, in both of this, ES as well as ESI, the substrate is bound with the enzyme. So it looks weird, but here inhibitor is actually increasing the affinity between enzyme and substrate. See, let's try to understand by the hypothetical example. Suppose in the absence of inhibitor, there is no any inhibitor, and let's say 10 ES complexes are there. But what will happen in the presence of inhibitor? So some of the ESI complex will be there. So let's say 2 ESI complex is there. right? But this ES complex will be always 10, right? So 2 plus 10 ES complex. So there will be a 12 complex in which substrate is bound with the enzyme. So as you can see, in presence of inhibitor, 12 substrate are bound with the enzyme. Whereas in absence of inhibitor, only 10 substrate are bound with the enzyme. So it looks like that affinity is increased. And whenever affinity is increased, that means Km is decreased. If you remember, higher Km means low affinity of substrate towards the enzyme, and lower Km means higher affinity, right? So this is the picture which we observed in the uncompetitive inhibition. Now, why we call it as a uncompetitive inhibition? See here, inhibitor is unable to compete with the substrate. Why unable? Because it needs actually a substrate. Once substrate binds with the enzyme, then only inhibitor can binds, right? Whereas in case of non-competitive inhibition, there is no competition because inhibitor has no influence on the substrate binding and substrate has no influence on the inhibitor binding. So there is clearly no competition. But here, in other words, in case of uncompetitive, we can say that substrate binding with the enzyme is actually helping inhibitor for the binding, right? So that's why it is called as a uncompetitive inhibition. Now let us try to see this thing in a graph. So the velocity versus substrate concentration, on the y-axis velocity V0 and on the x-axis substrate concentration. So in absence of inhibitor, the graph looks like this. So this is the Vmax, and this is, let's say, this is the 1/2 of Vmax, and the corresponding concentration of substrate. So the substrate concentration at the half of the maximum velocity is called as a Km value. Now let us see what will happen if we add uncompetitive inhibitor. So the graph will look like this, right? So the new Vmax is going to be somewhere over here. This is the new Vmax, and the half of maximum velocity, let's say it is over here. So 1/2 of Vmax. So the corresponding concentration of the substrate is going to be this one, right? So here, as you can see, the Km value is on the left side of the old Km value. So here we can see Km is decreased, right? So here there is a decrease in the Vmax as well as decrease in the Km value. Now what about lineweaver and burk plot or double reciprocal plot? So on the y-axis, we take 1 by velocity, and on the x-axis, we take reciprocal of the substrate concentration, that is 1 by substrate concentration. And let's say this line is in absence of inhibitor, right? So this y-intersect is going to be 1 by Vmax, and x-intersect is going to be -1 by Km. Here Vmax is decreased. So that means 1 by Vmax is going to be on the upper side, right? And over here, this Km value is decreased. So 1 by Km is going to be increased. So it will over this side, right? So if we draw a line, it will be parallel to the old line, but it is shifted towards the upper and left side. So such type of lineweaver and burk plot will be seen in case of uncompetitive inhibition. There is one example. Remember, uncompetitive inhibition is very rare in the biological system. The alpha ketoglutarate uncompetitively inhibits isocitrate dehydrogenase. So this completes our uncompetitive inhibition, and with this I complete reversible inhibition. In the next video lecture, we will look at irreversible inhibition and allosteric inhibition. I hope that all the aspects about the reversible inhibition is clear. If you still have any query or doubt, please write it down in the comment section below. Thank you.